In our last set of lessons, we'll be looking a bit more at nuclear physics, sort of the underlying structure of all matter in the universe. And to get a good grasp of what's going on in these modern physics principles, we'll start off in 1935 with Yukawa proposing the existence of what are called carrier particles. Now, these carrier particles are necessary for understanding physics because a question we haven't really addressed is, how does a proton know another proton is nearby? We talk about electromagnetic fields around these protons pushing on one another and repelling one another, but in reality, what is a field? It's just a magical, imaginary change in the environment caused by these positive charges. Why does the field increase as you get closer? Why does the strength of the repulsion change when you get closer? How does the moon know the Earth is there gravitationally? How does Earth know you're here gravitationally in order to pull on you? And of course, Earth's pull is relentless. You've never woken up one day floating about your bedroom because Earth forgot to put gravity on you. So how do objects know about the existence of other objects, and therefore how can they put a force on them? Yukawa proposed the existence of these carrier particles that transmit forces via the exchange of particles. In the electromagnetic forces, those particles are photons. Now we know an atom can emit a photon as an electron falls to a lower energy state. That photon can travel and then get absorbed by another atom further down. So photons can transmit energy from one atom to another. Well, Yukawa proposed that photons and other carrier particles can exist to exchange forces between, or forces are the exchange of these carrier particles between, well, it depends on what you're talking about. In the case of Yukawa, he proposed the existence of a particle called the pion. That the pion is a particle that acts as a carrier particle for the nuclear strong force. So in the nucleus, you have a bunch of neutrons and protons all stuck together. The protons, of course, hate one another and want to repel, but there is a stronger force than the electromagnetic force holding that nucleus together. It's called the nuclear strong force. And that the nuclear strong force, the neutrons and protons exchange these carrier particles called pions. The question is, where do these particles come from? Where do these carrier particles come from? And the answer is kind of interesting. It turns out they come from literally nothing. So what happens is the carrier particles can actually spontaneously pop into existence and vanish as long as they do not violate Heisenberg's uncertainty principle. Now, we talked about the uncertainty principle earlier, and Heisenberg's uncertainty principle deals with the idea between the momentum and position of a particle. But there's another version that deals with the energy and the time a particle exists. So the energy needed to create a particle, recalling that E equals mc squared, so the more mass a particle has, the more energy is needed to create it, times the lifetime of that particle must be greater than or equal to h, which is Planck's constant, 6.626 times 10 to the minus 34 joules times seconds, divided by 4 times pi. So, if you know what the mass of the particle is, and we know what the mass of a pion is, you can use this equation, again, coming down here, we can use this equation to figure out how long a particle can exist if it has a given mass. Or, if we know how long the particle exists, we can calculate what mass that particle must need. When doing this with a pion, it turns out that these pions that pop into existence spontaneously and disappear can exist for very, 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 very small amounts of time. So small that even if they're traveling at the speed of light, they basically can't leave the nucleus of the atom. Which is why the nuclear strong force has such a limited range. Because the carrier particles, these pions, are incredibly massive and therefore have very short lives. An analogy would be, not a great analogy, but an analogy would be, imagine you were a child, or say you have children, and you have a purse or a wallet, that has money in it. When you were a child, you might be able to sneak a penny out of your mom's purse to buy a piece of gum, and she might not notice that penny missing for a very, 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 very long time. Sneak a quarter out of her purse, you have less time before that's noticed, perhaps. Sneak $1 out, you have even less time. Sneak $100 out, you have very limited amount of time before that missing money is noticed. But the universe doesn't care as long as you put it back in that before it gets noticed. So the energy you can borrow from the universe, as long as you pay the universe back in a given amount of time, the universe doesn't care if you borrow energy. But the more energy, the bigger delta E is, the more energy you borrow, the smaller the amount of time you can borrow it before the universe notices. And the analogy might be, well, what if the universe notices? It can't. Heisenberg's uncertainty principle states it is impossible to violate this. Therefore, the universe never ever does. It's one of those laws of the universe, right? So the universe doesn't, oh, that particle exists for longer than it should have, therefore I will destroy it. Well, no, it has to disappear before the given amount of time. There is one way you can violate this. It's called Hawking radiation. We'll be getting into that, I believe, in the next few lectures. Or if we don't, you can look that up. So recall is misspelled. Recall. So here's our equation. So particles can pop into existence as long as they exist for a short enough amount of time that they don't violate the uncertainty principle. These particles, proposed by Yukawa, are called virtual particles. These virtual particles, again, don't exist for very long periods of time. We, by definition, can't detect them, because if we detect them, that means that they lived long enough for us to notice them, and they can't live that long. All forces, and we'll talk about the 4 fundamental forces of the universe in the next video, all forces have these virtual particles, carry information between themselves in an exchange of forces.